Well, hello there and welcome back to another video. So, we are back with some more advent of code, I think. In last video, what we did was to introduce some parallelism into our solutions for advent of code. So if we run this thing now, we can go do cargo, run in release mode, and well, it seems it was already compiled, so it's run right away. And you probably noticed that it was pretty fast. We can actually maybe build in release mode and then time the execution in target release advent of code. So yeah, it's taking around half a second, 300, almost exactly a third of a second, sorry, 334 milliseconds. And this is because we are running all the daily solutions in parallel, and we did that in last video. And now the total runtime is bound basically by the runtime of the slowest daily solution. So in this case, we can see that I think it is day 15 that is taking 323 milliseconds. And of course, this has some noise in the data. I run it again and it took less than 300 milliseconds. So the timings are not exact, of course, but they are roughly stable in the sense that the fastest solutions that take like less than 1 millisecond always take very little time, and the ones that take longer always seem to take longer. So in this video I wanted to maybe try to see what are the slowest days to compute and see if we can do something about them, like maybe parallelize their implementations or use some clever optimization or something. My main two ideas would be to either use Rayon for parallelization or use fxhash, which is, maybe I can open it in the browser, Rust fxhash, which is basically just a hash map and hash sets from the standard library, but with a different hashing algorithm, which is faster. I have my TV turned on the background. I will pause the video for a second. How was the pause? And I'm back. Sorry, I just wanted to turn off the TV. So yeah, as I was saying, fxhash might be a good candidate for as a replacement for the standard hash in the cases of problems that might do a lot of hashing. I don't know if we have any of those taking much time, but well, it's a candidate for optimization. And by the way, I have been playing a little bit with profiling these things. So, but I haven't got really good results with that. If we run, for example, well, let's first fire up the code editor. So for profiling, you need to enable something in the cargo file, which I won't remember. So let me Google that. Again, let's look for Rust profiling. I have already been reading a little bit about these things, but yeah, this is what I want. On the release build, enable some debug symbols. And with that, I think we can build for release again. That is a bit strange that it didn't rebuild and I changed that. That's kind of weird, right? What if I build... This is already a bit weird. I would have thought that this would have like force the rebuild. So if we do, is there some clear or clean? Yeah, clean. Let's clean and let's rebuild. Yeah, I trust this a bit more. And then, well, it takes a while. Then we can do use the perf command. That is something that comes in with Linux, or doesn't come built in, but you can install it, and uses some kernel magic to profile the program while it's running. Like it checks. It's the classic like sample profiler that every once in a while takes samples from the running program and sees where the code stack is, and then you have like a call graph or a flame graph or something like that. So we can do perf record -g is something for flame graph, I think, and then what you want to run. So this will be target release element of code. Let's run this day 15, which was the one that was taking the longest, I think. Yeah, day 15. And if we run this, we actually get an error because you need to run it with sudo. I have no idea why. Let's just do it. This thing then generates a perf data file, which you need to also convert with another command that's called perf script. This will implicitly read from that, and you have to give it, well, you can redirect the output to a file. Let's call this file day15.perf. Okay, let's do this. So this file, where is it? Day 15. Okay, 180K. Let's open this, and there is a online profiler from Mozilla that lets you visualize these things without the need to install some extra application for it, which is nice. So, can I increase the size of this? Okay, here we can see, like at least for this problem, which I barely remember what it is about. It was the beacon exclusion zone. I remember that it was pretty fun to do. Oh, and there is a hash set being used here. So what we can see is that most of the samples fell into, it's not 100%, but well, of the samples that were captured, reverse for push, okay, quite a bit of malloc, okay, but yeah, most of the samples fell into this get contiguous exclusions row segments, which I think is this thing. It does do a little bit of dynamic memory allocation, but the main thing is that it's also being called many times, I think. Yes, by this thing. I think this was like part 2. Beacon X, beacon, yeah. This was for the answer of part 2. We are executing this function 4 million times. So it's not surprising to see this on the profiler, but to be honest, I don't find anything very useful here in this information. So I'm probably not going to be looking at profiler data. I'm just going to try to analyze the slow solutions kind of by gut feeling and reasoning. So in this case, yes, running something that is, even though it might be quite trivial, run it 4 million times might take some time. And I seem to remember that in this problem, when I solved it, I had the idea that we could probably have like a much better algorithm to do this, like a much clever solution. So you're basically finding like a single beacon, or yeah, like a single point in a 4 million by 4 million square, by finding the only point that was not covered by some sensors. And these sensors had like areas that were like squares but rotated 45 degrees, so they are like diamonds. And to find that, what we are doing is sort of a brute force. On each line we find which segments on that line are covered by sensors, and usually that is the whole line is covered, but in one of those 4 million lines there are two segments that are displaced by one, like they are not touching by one point. And when that segment is found, so in this case what we do, if the end of the first segment is less than the size, we know that there's only one line where there are two segments and there is a single point that is missing there, and so there we found that solution. So it's kind of a brute force thing, and I think we can probably, like there probably is a much better, much more clever way of finding this, by thinking about the areas of these diamonds. Like for example, what I was thinking back then was, if you consider like, when can it be that you have a point that is not covered by any sensor? When you have two sensors and their areas almost touch, but they have like a line, a diagonal line that is not covered. So basically their distance, the distance of those sensors is the same, is exactly the range of both of those sensors added together plus one. So that one is the gap between those two. So only in those cases you will have like a line of a single diagonal line of uncovered tiles between those two sensors. So those pairs of sensors are like candidates for where this point might be. And if you find those diagonal lines, and you find all of those diagonal lines, and you find the lines that cross, well, the two lines that exactly cross, I think if you find that will be the exact point. I'm not exactly sure, and I didn't try to program that because it's a bit of 2D math reasoning that I don't know. I haven't sat down and thought about that, but I think that this brute force solution can also be optimized, probably, because this is a linear search, what we are doing here, and we can probably parallelize this using Rayon. So I will first try to do that, and maybe leave for another time the idea of finding a better algorithm. So how do we parallelize this linear search with Rayon? By the way, I'm probably going to get rid of this. What changes do we have? Oh, yeah, these files. Okay. So for some reason here I used a for loop. So the first step would be to change this into an iterator-based solution. So how do we do that? Well, we can map these things to the segments, I guess, and then find something, yeah. Or even, so okay, let's first run this. If we do cargo run in release mode for day 15, it is compiling again. I don't know why it needs to recompile everything. Maybe this time it actually took heed of the change in the cargo toml file. But yeah, okay, it's taking like 300 milliseconds with a bit of variance in those runs. Okay, So what if we change this and the answer is this big number? I also wonder if I could maybe add like the sample test for this, because we don't have. If we go to Advent of Code 2022, day 15. Yeah, we do have a sample. We could have a test for that, but I'll just check that the numbers are still the same. How do we rewrite this as an iterator? I guess we can start by saying, okay, this thing, what I'm basically doing here, I think is just a map and find, and I think there is a find map function. So this is the y coordinates. So we want to find the y coordinate that's where this is true, basically. Right? Yeah. So if end x is this, otherwise it's going to be none. And this already returns an option of a point, so type of this should be fine. And is that it? That seems way too easy. Let's run this now. Okay, yeah, the answer is still the same. The runtime didn't seem to change though. Well, that was a bit faster. It seems to be running. Maybe I'm just tripping because of the. Yeah, maybe it's just a random noise there. But like, I don't think this should be anyway faster because it's basically the same thing rewritten as an iterator. Instead of a for loop. So okay, we have this. Can we change this into a parallel iterator? And again, I know that I need to import everything from Rayon Prelude. There is no find map. Why not? Isn't there some way? Okay, yeah, Rayon has this find first or find any because the iterator is parallel. So when you have a sequential iterator, find will find you the first occurrence of this. But if you have parallel iterators, you might want to find the first one or any of the items in that iterator that matches this function, this predicate. So in this case, it should be the same to find any or find the first, because there's only one. So I would say maybe find map any and see what happens now, and we can see if finding the first one does make a difference. Whoa! Look at that. Oh, actually, there's two things to be surprised about here. One is that it's much faster. That's really great. That's awesome. And let's see what happens if we find map first. Because this will need to actually consume everything. Yeah, so it is a bit slower, almost double slow. So let's find any, because it should be always the same. That's great. And the other thing that I'm surprised about is, like, we are doing a parallel iterator over 4 million elements, and Rayon doesn't break sweat with this. That's awesome. You know, if we were doing the naive thing of launching 4 million threads for this, I think we would hit some OS limit or something, like too many threads, or it would be much more expensive to launch all those threads than do the actual computation inside of those threads. But for Rayon, it didn't seem to make any difference, and that's amazing. Huh. One thing that I was thinking of maybe trying was to do like a chunk iterator, like iterating these things in chunks of, say, I don't know, 1,000, and then parallelizing those chunks, and within each chunk of 1,000 do a sequential search. And I don't know if that would be even faster, but this is great already. Like this is already quite great. Let's actually try out the chunk idea. So how would it be? I think I need to first chunk this. Is it chunks or? I thought it was chunks, but maybe I am exact. Are you auto-completing here? Yes, you are, but there's a step by. I don't know if this is what I want. So what do I want actually? Maybe I can write it manually. Although there's no chunked iterator, I think, because that would probably need some sort of allocation. Yeah. Let's say chunk size be 1,000. So let's do. What do I want to do? From 0 to up to and including or not including size divided by chunk size. Yeah, we would like to have this into a parallel iterator, I think. And then we would like to find the chunk inside of this, so find map any. Yeah, this is not the y, this is the chunk. Yeah, chunk number or something. And then we would like to do for 1 up to chunk size, find, do a find map here. And this would be like the offset inside of, I feel like I'm doing something kind of stupid here, but let's comment the old code that we know works. And the y coordinate then would be the chunk times chunk size, yes, plus the offset, right? And then it would be just the same code as before. I actually don't know if any of this makes sense, but well, I think that's a chunked iteration. Not really sure. Let's run it and see if we have the same number. Yeah. we did get the same number for some reason. But what about the runtime? The runtime seems to have improved a little bit, or not. Maybe it's a bit random. So what if we, if we go down to a chunk size of 1, it should degenerate, and probably it will be less efficient because of all the calculations. But yeah, it's basically the same as the Rayon naive parallel iterator solution. What if we go up to a bigger chunk size, like, I don't know, 100,000. Yeah, nothing seems to make a significant difference here. So I guess if I go up to 1 million, then it will degenerate because it will be like only 4 parallel iterators and then a sequential search of 1 million. So in this case, I would expect this to grow. And yes, indeed, it is running a bit slower. But yeah, it doesn't seem to make a whole lot of difference, you know, how much. So maybe Rayon tasks are really, really inexpensive, like really, really cheap. This seems to be a tiny bit, you know, with chunks of 1,000. It seems, maybe it's just noise. Yeah, it seems to be noise, actually. If we comment this and go back to the naive and very nice code of a parallel iterator, yeah, it actually seems to be faster or the same. It's just the same. It doesn't make any difference. Okay, I think that's great, actually. We don't need the complexity of trying to chunk the iteration of this. And yeah, this is great. What are we doing using the hash set for? Exclude positions, count at row. Yeah, this seems to be for part 1, but I don't think that this is any performance bottleneck, so I will leave it as is. Okay, what happens if I actually profile this now? Let's actually get rid of maybe these 2 files. Yeah. Let's do a record again. Oh, I need to enable the debug symbols in cargo toml. This thing, okay. Before doing this, let's do a cargo build release. I'm not trusting this build because it's not rebuilding the dependencies, but okay. Let's do a record again. I wonder if the different threads will appear in the profile. There were quite a bit of samples, almost the same as before. We run the script, yeah, again with the same name, but for some reason permission denied. Do I need to be sudo for this? Cannot override. This is a no clobber configuration that I have on bash. Okay, yeah, let's open this folder again. Go to profiler.firefox.com and let's see this. Yes, we actually have the different threads here. That's awesome. How are these called? Interesting. Yeah, different threads, it seems. And now most of the samples are falling into things that I don't know. Things that I don't understand. Can I invert this call stack and I have no idea what Intel PMU enable all and this kind of things are. I don't see anything related to my code. I wonder if now the main bottleneck might be the communication between threads, but no, that doesn't seem to be the case, because when we try to do a chunked iteration, we didn't see any difference by doing like internally sequential searches. So I don't think that is a problem. One thing that I don't particularly like about this is that this function, that is the one that's being called 4 million times, or possibly 4 million times now because it's in parallel, and it finishes when any of the threads finds something. But what I don't like is that it's using a dynamic vector for this, and I'm pretty sure that most of these return values are just vectors of 1. But I think internally, yeah, like we have these segments, and yes, we push and pop from here. So this thing may internally grow a little bit, but in the end, it's like all of the sensors like gets coalesced into a single segment. Yeah, I don't think we could optimize that. Maybe I could reuse the buffer, but now we have parallel iteration over this, so reusing that is not a good idea. So okay, I think that is a good optimization for day 15. And actually, I should try to run time the running of everything. Yeah. So now running everything is taking less than before, because now the day 15 is no longer. Oh, but look at this. When running day 15 alongside everything else, it no longer takes that little. So if we run day 15 like this, yeah, if we run it alone, the time reported here is matches the time reported by time comment, 30 milliseconds. But if we run it with everything else, this is quite interesting. It still takes quite a bit, and this is because, well, it probably cannot use the full thread pool to run its own, because the Rayon thread pool is also running the other daily solution. So that is pretty nice. I think that's pretty interesting. Like it's probably doing better utilization, and I wonder if this will actually impact on the recording of this, because I'm like OBS that takes quite a bit of CPU when recording. So I wonder when I'm running this if I will get some drop frames or anything, or glitches in the audio. We shall see. But yeah, for now this is a good optimization, and I think I will actually commit it right away, because yeah, it's actually a pretty simple change here into pariter. I do want to ask the Rayon documentation though if that is the canonical way of converting a range to a parallel iterator. Rayon parallel range. Rayon range. Okay. Yeah. Okay. seems to be the case. Yeah, it seems to be the case, into par iter. Okay, let's commit this. Optimize or improve runtime of day 15 solution by doing a parallel search. This cuts down the runtime of this single day from around 300 milliseconds to around 30 milliseconds, or around 100 milliseconds when running with the full suite. Yeah, of daily, yeah, days, whatever. And commit. Okay, let's take a look at the next bottleneck. This will be what? Oh, maybe day 16, the next one. Day 20 or 23 or 24. I'm a bit scared about 23 and 24 because these were like the last days and they're usually quite gnarly, but they seem to be actually the ones that are taking longer. So let's take a look at the 23. What was this about? Unstable diffusion. Yes, this was the one about the elves moving around the map. This thing uses a hash map for the proposed moves. This is interesting. Yes, and I wonder if parallel iteration can be achieved here, or if it makes sense, because we are also looping. We are looping some amount of rounds, and actually the total rounds is what gets printed in the end. So this day 23 is running 1,000 rounds, and this loop of rounds I don't think it's parallelizable because yeah, the elves are kind of diffusing around the map, and each iteration depends on the result of the previous one. So it's not something that you can compute, all the rounds in parallel or something like that. But maybe we can do some parallel iteration within each round. Like here, for instance, this first part was the elves deciding where they want to move and proposing moves for that, and then iterating all the moves. These are very well. Actually, these could probably be rewritten. It is written as a for loop with a side effect of writing into this proposed move hash map, but probably it could be implemented as directly as a non-side effectful, like as pure mapping of these elves, like map each elf to its proposed move, and then collecting all of those moves into a hash map or something like that. That could probably be done. This iteration, though, doesn't seem to be a good candidate for doing it in parallel, because we are iterating only to write into the map and into this elves vector. It is a vector, right? Yeah. Okay. And we have these proposed moves, which is a hash map. I wonder if it makes sense to maybe try fxhash for this. Or also, one thing that we are doing here, like for the map and for the elves, these are data structures that live that are kept alive throughout the execution of this program and throughout the execution of this loop. But the proposed moves is a local variable inside of each loop iteration. So I wonder if it makes sense to share the data structure, because I think if we can clear up and reuse the hash map, so it doesn't, dynamically allocate memory on each round, maybe that could save us at least dynamic allocation. So if we move this out of the loop, and at the end of the round, so this is the break condition. At the end of this round, what happens if we... Okay, yeah, if it is empty, it means that no elf moved. So that is the break condition. What if we do propose moves clear? What does clear do? Clears the map, removing all key value pairs, keeps the allocated memory for reuse. That is exactly what I want. What does this do? I should probably first run this before making this change. Run the single day to have an idea of how much time it takes to run. Cargo run release mode, day 23. I run the day on its own, so it's taking around 200 milliseconds. Yes. Does this make any change? Moving this outside and clearing it after each round, because maybe clearing the data structure might also be expensive. So maybe this won't be any better, or maybe it is. Yeah, look at that. It seems to have made it at least a little bit faster. Not a whole lot, but somewhat. Yeah, by just reusing the memory, which sort of makes sense. Actually makes sense. So this is already some improvement, but I also wanted to try to use fxhash. So let's also maybe give that a try and do cargo add fxhash. Okay. And if we do just fxhash map new, can you suggest importing? Yes. fxhash. We should no longer use this. And new. No function. What? There's no new in fx. What? Yeah, fxhash map is just the hash map from std with this hasher. So doesn't hash map have a new function? I don't understand this. What's happening here? So wait, let's have both imports. So hash map new does work. And what is this? It's just the default. Is this only an implementation with this state? Maybe it is. But the implementation just does default. So can I change this to fxhash defaults? Okay, it seems I can. Perfect. What happens if I run this now with fxhash instead? And it doesn't seem to make a difference, or maybe a slight one. We were running, yeah, a bit over 150 milliseconds, and now we are a bit under that. It's not a huge difference though, but maybe most of the, probably most of the runtime is not spent on hashing, it's just everything else. And if we move this thing inside and not do the clear, does that do any difference compared to the original, like 200 milliseconds? Oh yes, it actually does. Quite a noticeable one. So fxhash is faster than the standard hash. And I don't know if it makes any difference to move it outside now that I'm using fxhash map. Maybe a tiny bit, but maybe this is just noise. Although it seems a bit faster. I think I would leave it as this. It also makes some sense to reuse this data structure. It's not too bad. And I would like to check some of the documentation of Rust fx hash, because I seem to remember that the idea is to the idea of its use is to import things and rename it as hash map. So then you can just use it with a name of hash map, but I'm not sure. Let's check the documentation. Yeah, beautiful documentation. Brutally effective hash function. Okay, maybe this is what I saw. Importing this as hash map. I don't really care about the difference. Although maybe, let's actually see if I rename this to hash map here, does this rename the imports? No, what does it, is it trying to use? No, this is not what I want to do. I just want to rename the import here. Factor, yeah, continue. Let's see what happens. Yeah, but this is not what I want. This is broken. This is the kind of thing where language server could be improved. So I want fxhash map as hash map, and then just use this. Okay, it's just an aesthetic superfluous difference. Okay, so it seems to have made a little bit of a difference. What happens if we time the whole thing now? Oh, look at that. We were under under 200 milliseconds, and probably if I run this without recording, it will be for sure under 200 milliseconds. That's great. That is great. So let's check the difference here. Yeah, use this and reuse. Yeah, that seems like a reasonable change. The cargo log file, I guess, now has the fxhash, and this thing I want to not commit this, but do commit the fxhash, and probably let's also go to the README and keep some honesty here. Use vanilla Rust, no external dependencies. With a couple of, except for a couple of exceptions. Rayon, which is awesome, and fxhash, which is just the standard hash. Yeah. Hash, yeah, but faster. Standard hash set and map, but faster. Okay. I think that is okay. Is this the name of fxhash? I think it's simply with lowercase, so let's use that name. fxhash. Yeah. All right, let's commit these changes and say improve performance of day 23 by using fxhash and reusing the use fxhash instead of std hash map. And reuse the hash between rounds. Okay. Oh, all right. That was quite nice. Let's keep it rolling and see what is the next slowest day. So interestingly, also day 23, when running it with everything else, is taking quite some time. So we are like also pushing the limits of like what my computer can do in parallel, which is interesting. Although it's not very consistent in, yeah, I guess that also depends on which thread it is falling into or when it is running, but yeah. So it seems like day 16 and 24 are the next slowest. I don't remember what they were about. 24 is Blizzard Basin. This one was quite entertaining. This is the one that you are running around on a map that has blizzards and you have to avoid those blizzards. And this is using Dijkstra, shortest path. And I think like the bulk of the work in here is done by this algorithm. Maybe we can optimize some of this next moves function, but inside, and I'm pretty sure that inside of Dijkstra we use a couple of different, quite a bit of different hashing things. I think the main guy here is the binary heap, which we keep the unvisited, like it's a sorted collection, and this thing needs its elements to be comparable. which I think we implement in this node thing. Yeah, we implement the ORD and partial ORD traits. I don't remember why we need to do both, but that's what we do. And we only compare the distance, yes, okay. But we are also using a hash map to keep the distances, and that's interesting because we need the elements that we are visiting here. So shortest path is like a graph traversal, like how are these things called? Like minimal path algorithm. And the T type here are like the nodes that we are visiting. And we require a couple of things from them, among others, for them to be hashable. So I don't know if using fx hash map here would work. Let's try it and see if it makes a difference. Yes, import this thing. We know that this doesn't work. We need to call default. And it seems to compile. What does this thing requires of? It's k. I guess it's the same thing as hash map requires of its. And there's a base hash map, which we cannot see. Okay, great. I am surprised that this thing might work with things that implement the standard hash, although this trait is, yeah, just this. Okay, I don't know if this will actually make any difference, but we shall see. We shall see. Let's run it. Oh, it was not running the day 24 in isolation. I want to first do that. So let's go back to the original and let's run cargo run the in release mode day 24 to see how long it takes in isolation. Around 180 or 90 milliseconds. Let's go with the fxhash and see if it makes any difference. I don't expect it to, but it does. It actually does. That's very interesting. And I do wonder, because this thing is also being used in other days. Among others, day 16, which is the other one that was slow. So it did improve the performance of day 24, going down from 190 or 180 to 130 milliseconds. And what happens with day 16, I wonder? Let's go back to the other version. Let's run day 16, which I don't remember what it was about. It is Proposidea Volcanium. And what was this? Oh, this is the one that I was too stupid to implement on my own. Well, I did do an implementation, but it was horrible, and then I ended up looking for another one. And I copied this thing from Reddit, but converted it into Rust. So yeah, I think this is basically also uses shortest map, but I think this one is using shortest map for something very silly and just as like a pre-process kind of thing, so it won't affect the runtime here, I think. So day 16 is running 190-ish, 80-ish milliseconds, and if we change Dijkstra to use fxhash, and by the way, I'm not even checking if we are getting the same answers. I assume we are. It seems to be the case. But yeah, it doesn't affect the runtime. It may be even increasing it, or it's just noise. Yeah, no, it shouldn't affect this because in day 16 we are just using the shortest path for something that is not really the bulk of the problem. Like this is a pre-processing thing. But for day 24, yeah, the shortest path is the bulk of the problem. So optimizing that does make some sense. And that is great, I think. There is something that I don't understand though about fxhash. So we have this. Does it make sense to we are hashing, what are we hashing here? Distances. Yeah, and we are using these nodes as keys to see how distant this each node is. And so basically the nodes know how to hash themselves, and I wonder if they would use like instead of deriving the standard hash, they would use the hasher from fxhash. If that would make some sense. And there is also built-in functions for this. Interesting. And this hasher. I wonder if there is a... I don't know what happened there. Oh, I just fucked up the window. Derive hash. Is there something like this? Because what we are passing here as states in this day, no, not day 16, day 24, the starts. Now what we are passing are tuples, and these are basically two 32 integer numbers and one 32-bit integer. If we change this to be 16-bit integers and the 32, they basically, the whole tuple would fit in 64 bits, and we can probably use that hasher from fxhash, and it would make more sense. Though I'm not really sure. I'm not really sure about that. I will have to investigate a bit more. But this seems to be like a safe change to make our Dijkstra algorithm a bit faster. And does this affect the whole thing if we run it like this? Doesn't seem to. Although, yeah, day 24 is now faster. Yeah, now it seems like day 16 is the bottleneck. So we did make day 24 quite a bit faster, actually. Yeah, I like that. That is really nice. Because these are the next moves thing. I don't think there is that much to do here. There are quite a bit of accesses to these. I would trust the optimizer to be inlining all of this width, height, and blah blah blah. This thing can also probably be used here. Let's see, actually, if we extract width and height here and use this for the bounce check. So this, we will also make the code a bit more readable. So the bounce check uses these outside variables. This shouldn't make any difference, I think. I would trust the compiler too. Yeah, no, it shouldn't. Although, nah, it's just noise. Yeah, compilers are really good. This kind of thing doesn't make much sense. Yeah, and I cannot think of any like algorithmically interesting optimization to do here. These three things cannot be run in parallel because they depend on each other. Like they use the result from the previous one. So that's also not something that could be done. Dijkstra might be parallelizable, but that is not something trivial, I think. Okay, and which one was the other day? Day 12, but I don't think day 12 is taking long, right? Yeah, no, it's just 1 millisecond, so it's not making any difference there. Okay, but this seems to be an okay optimization for day, what was it? Day 24, yeah. Yeah, let's commit this. Improve runtime of day 24 by using fxhash on Dijkstra's algorithm. That's always a difficult name to write. This, well, let's just say use fxhash on blah. This improves the runtime of day 24 from around 190 milliseconds to, what was it? I think around 130. Oh, did it become slower? Oh, was it actually faster when I... Wait, did that change of extracting the width and height actually make something? I'm not sure now. Let's copy this commit message, but not commit. I mean, I am sort of tripping now. No. What the hell was happening there? Weird. But yeah, it seems to go down to around 130, I would say. From this to 130-ish milliseconds. Okay. Let's maybe take a look at one more, because I want to also go and do something else. If we time the whole thing, what is the next slowest one? It seems to be day 16 now, by quite a bit. Yeah. And day 16, well, it is the one that I couldn't really solve, so or I couldn't solve in a timely manner. So I really doubt of my capability of actually improving this. So what were we doing here? Part 1 answer and part 2 answer. Part 1, yeah, this one was about visiting all the paths inside the graph and trying to find, like, opening valves and something like that and releasing pressure, something like that. Yeah, pressure release and all of this. This one was a very hard one. I do wonder whether part 1 or part 2 is the slowest one. So we are using this visit all paths, we are calling this twice. One with 30 minutes, I think it was, or remaining minutes, yes. So the idea, I think, in the puzzle was that you had 30 minutes to open valves inside like a cave, but then an elephant can help you, and you have 26 minutes to do it alongside the elephant, and you want to see how many you can open, both of you at the same time. So what happens if I comment part 1 and only run part 2? Like, where is the bottleneck? And I actually should be running this. Let's see how long it takes in isolation. Around 180 milliseconds or so. Let's comment this and only run part 2. I would guess that part 2 is the one that is expensive, but I'm not really sure. No, actually part 1 also is comparatively expensive. Part 2 is also doing this. So part 2 is doing 2 things that I'm interested in. Yeah, part 1 is like 50 milliseconds of the 180. So I guess the cost to visit all paths are, you know, the expensive things. But then part 2 also does this double for loop inside of, like, yeah, it's like an inner join between all the pairs in this part 2 pressures, and tries to find the ones where these bit masks don't overlap. So it's doing a bitwise and if it is 0, they don't overlap, and then it's taking the maximum of those pressures, the sum of those 2 pressures. So this can probably be expressed as an iterator. Maybe this can be parallelizable, but I don't know. Is this actually expensive? Let's say that part 2 answer is actually part 2 max pressures length. So it's, you know, it computes this thing. And actually we can also see how many of these pressures are. So, you know, when we are doing this double for loop, like, what are we dealing with? So if we skip that double for loop, oh, look at that. It's actually, yeah, that double for loop is actually quite expensive. And we are printing this length as the part 2 answer. So that is 5,000 and something. 5,000 times 5,000 is like 25 million, if I'm not mistaken. So 25 million is quite a loop. And this is a nice candidate to parallelize. Indeed, it is. Yeah, that seems promising, actually. So let's go back to this and think about maybe parallelizing this. So it seems like, yeah, visiting all paths, which makes sense. You know, the part 1 is taking 50 milliseconds, but we saw that when running those 2, it was only taking 60 milliseconds. So the part 2 call to visit all paths is taking just 10 milliseconds, or it's taking less than part 1, because this is calculating all paths using 30 minutes, and this is just using 26 minutes. And visit all paths. Yeah, this is also using this hash map as a mutable parameter here, and then calling itself recursively, which I think is doing sort of a depth first search. But I wonder if this thing can be rewritten into like a for loop instead of a recursive thing, and have this max released pressures hash map, be a local variable and just return it. Because I find it quite ugly that this thing is used like a sort of as an output parameter. But yeah, that doesn't have anything to do with this optimization that we want to do now. So what are we doing here? We are iterating over this, and then we are iterating over this. And we are basically wanting to find a maximum of these two. So how do we express this? I think with parallelizing the first loop, the outermost, it will be enough. I don't know if there is like Rust all combinations of elements, because that's basically what we are doing, like a Cartesian product between all of the elements in this set, this collection. And then we trying to find the ones where the intersection is null on these two bit masks. These are just 16-bit integers. I doubt that this is... Oh, is this combinations a thing? No, it's asking if it is a thing. Yeah, and unsurprisingly, it is a thing in iterators. But I think I have already added too many external dependencies with Rayon and fxhash. Iterators is something that I think it's a line I don't want to cross. So is there a better solution not using iterators? Look at this. This is promising. Someone on Reddit just asked this. No. Okay, no worries. We can probably write this ourselves for this special case. So we want to find basically a maximum on here. I think we can express this as an iterator, flat map it, no, not flat map it, or yes, flat map it with this, and then find the maximum, maybe. Could be. Let's see actually the answer. Let's run it again. So I think this is the maximum release pressure when doing it on my own, and this is when doing it with the elephant. So 2838. Can we do something like part 2 answer will be just this iterator, then flat map. Is it a flat map? I want to, yeah, basically join each of these elements with this is a pair of bit mask and pressure. We close the iterator here. And what are we flat mapping to? We are flat mapping to the same part 2 max pressures iterator, and we are going to map each of these let's call this thing pair 1. We're gonna map with pair 2 and just have a tuple with the 2 pairs. So pair 1 and pair 2. And that's what we are going to flat map into. Then we want to make this combination. We want to filter out, yes. So let's get rid of this. This is a flat map. Then after flat mapping, we want to, I don't know what did I copy. Yeah, I did copy the correct thing. We want to filter with some predicates, and that some predicate will be basically this condition of the bit mask not being 0, and in that case we are going to map to the sum of the 2 pressures, and we are going to take the maximum of all of that thing. Right? Maybe we can express this as a filter map. No, let's just do filter first. So this is couple of pairs. So each of the elements is going to be a pair on itself. So we have, what was it? I think it is, I don't remember the old code actually. Yeah, bit mask is the key and the pressure is the value. So we have bit mask 1 and pressure 1, which we are not going to use, and bit mask 2 and pressure 2, which we are not going to use. So we want to filter the ones that the intersection is 0. Okay, and then we want to grab the map this. This is kind of a very messy chain of iterators, but if I get it right on the first try, I will be happy. We'll see the parameters then, but we just want pressure 1 plus pressure 2. And this is basically the same parameters as before. But in this case, I don't care about the bit mask. So bit mask 2 and bit mask 1 I don't care about, and we have pressure 1 and pressure 2, which we do care about. Okay, and this is probably not possible because we need to dereference some of these things. So this is a double reference. Why? Because we are flat mapping into these things. I probably want to dereference this. Okay. You don't like this because, wait, isn't this something that we can do? It's not like this, right? No. Why don't you like this? Huh. Okay. So pair 1, it is, it's a tuple of references, not, okay. So I cannot dereference here, right? No. Okay. So then, it will be double references, which is kind of a pain. Can I dereference at least at some level here? Yes. And then we have pressure 1 plus pressure 2. Okay, we have this, and then finally we're going to take a maximum of those sums of pressures, right? Yes. And we're gonna do unwrap or just 0. What about that? That's very messy. Yeah, you don't like this, which is, yeah, it sounds okay, yeah, but I want to make a copy of part pair 1. Won't you let me do so? Can't I? Yeah, dereference. That's the thing that I want. Cannot be dereferenced. Yeah, no, I know. But bitmask 1, pressure 1. This is references. Okay. Can I dereference here? What about doing bitmask 1, pressure 1? Wait. Let's go back to this. Can I move here? Yes, okay. Let's keep it like this. We can think about improving that later. So, is this still the same? Yes, the answer is the same. And we might actually have improved performance a little bit with that, or maybe not. Maybe not. It's just the same for loop as before. But now we should be able to say par iterator here. This comes from Rayon, and Rayon imports everything on the prelude. And par iterator doesn't have flat map. Why not? Wait, it does have, but it does have also a flat map iter. What's the problem here? Oof. Okay, we are returning probably this iterator mapped as this. Okay, it's not as easily parallelizable. Okay. Does it work if I do par iter inside of here? Magically, it seems to work, but I'm not really sure if I want to do both par iters. Well, let's see. Let's see what happens. Let's see if this gets faster. It did get faster, actually quite significantly so. It didn't get simpler, to be honest. This is much uglier code than I had before, for sure. But it does run faster. I don't really like this change of using iterator and flat map instead of the double for loop. I think the code before was quite easier to follow. I do wonder if I although it does it does get the same results, and it is faster than before. If we run everything now, what was this thing? Day 16. Well, now we are basically facing, well, day 23 is now the bottleneck. But yeah, we have pushed this to under 200 milliseconds almost for sure. So that, I think it is quite a big improvement. And it was quite a nice exercise of parallelization and some optimization. I'm not really sure about this thing though. Let's do something. Let's add these changes temporarily. And let's think if we can use a parallel iterator on the outside. And what do we want to do here? I think we are having all the pairs of this thing. So the flat map isn't actually that weird, right? I don't think it is. Yeah, the filter gives us a reference to those pairs, so the reference in here does make sense. The mapping, though, I'm not sure what I'm getting, like a tuple of references instead of, well, I guess that is what the iterator gives us. Yeah, the iterator of the hash map. That is fine. That is fine. So another possibility is to map into the maximum pressure of what do you want? Maybe the maximum of the second pressures, and then do the addition. I think something like that could make sense. Although we need to do this filter. I don't know. Like let's try something instead of just thinking in the air. Instead of doing flat map, I want to map into. Here we will have. Let's name this thing bit mask 1 and pressure 1. And we are going to grab the map part 2 max pressures, iterate over them. I guess here inside of here we could do like a for loop like we were doing before, but let's do it with iterators too. We're just not going to do the mapping here. I think what we want to do is find the part 2 max pressures that comply with this. Bit mask 1 and 2 are 0, right? And the parameter here are gonna be bit mask 2 and pressure 2, and then you're going to map this to what? Same parameter here. I guess you're going to map this to pressure 1 plus pressure 2. And of all of these, we want the maximum. And wrap or 0, because I think now it could be 0, because this filter might filter out everything for some of this this bit mask 1, and then we don't need to do this filter here, we don't need to do this map here, we are getting the maximum. Yeah, that sort of makes some sense. Bit mask 1, 1 one of these is a double reference. Let's not be so. We have unused things, sure. Mark them as unused. Maybe I could do a filter map here, but it's not much of a difference. How does this run now? And how was it running before, actually? Like in 100 milliseconds. And it actually seems to be a tiny bit faster with this, and the answer is the same. And I find this thing to be a bit more similar to what we were doing in the for loop before, like the nested two for loops. So it's not too bad. We know that, what do we have here? We have this map and this filter. Yeah, this could be, you know, the maximum could not exist. This would be an option. So this could be a filter map simply. Yeah, that is a simplification. To not do the unwrapping twice. And also, what happens if instead of taking the maximum here, we just map to everything and use a flat flat map? If we do a flat map of this, we're gonna get just numbers of the addition of, but I think this is probably, yeah, the same thing as before, that we need a parallel iterator over here. And now what's the problem? Closure outliving things, because these are all references. Help me with moving stuff. The move keyword is magic. It's not magic, but it works kind of like it. Okay, this actually does work a little bit, and it is somewhat more understandable in my head. Finally, this might be a good case for doing filter map, although I'm not sure. If we do filter map and we have these two, we can say, okay, if this is the case, then return sum of pressures, else say none. And in this case, since it's not a filter, it's a map, do we still need the move? Yes, we do. And do you like this? Yeah, it's, I mean, it's not really that much more readable than the filter and the map. So maybe I will go back to that. Okay. Yes, but I think this is sort of more understandable now. We have a parallel iterator over this. We are flat mapping to get all of the pairs, all of the added pressures where the bit mask don't overlap, and then we are getting the maximum out of those. I think that makes some sense. And this does improve the runtime of day 16. Yeah. And if we time everything, yes, we are under 200 milliseconds, actually about 150 normally. That's really nice. I think overall this was a nice optimization session. We still have the worst one now is what? Well, it's no longer day 16, which I was very I was a bit concerned about, because this thing is doing something that I don't really remember, and it was kind of a mess. But the bottleneck was in this double for loop, which was relatively easy to parallelize. So that's fine. And I think, let's check something else first. If we change these parallel iterators to normal iterators now, this thing still compiles, and it should still have the same result as before, it's just being a bit slower. Yeah, look at that, that's awesome. So I really like this kind of, actually, I will do this. Let's do first a commit, or let's first check the difference of this and the for loop. Well, I think the for loop was probably quite a bit more readable, the double for loop, but it's not that much worse, and it's more functional, let's say, less imperative. So yeah, we'll have this, and I won't do two commits, but I will be satisfied to know that if we change these parallel iterators to normal iterators, the thing still works with the same results. Yeah, and these imports, like the way what are we using mem for? Oh, awesome. Bitmask bits, that's, I don't remember why we needed that, but let's not question it. I will question though the automatic imports of this thing. Oh, and I saved and it reordered something, so okay, let's go with that. And commit this. Improve performance day 16 by using parallel iterators. All right. It wasn't a huge improvement, but it was significant. And overall, we decreased the total runtime from, I think, like a third of a second, like 330 milliseconds or something, to almost half of that, or even less than half of that. So I think that was a pretty big win, and yeah, I think a nice learning experience of when to use fxhash map, or like a better hash algorithm, and when to use parallel iterators and things like that. So yeah, I think it was a pretty nice optimization session of today. Let's call it a day, and let's maybe write video thumbnail. What did we do today? So let's use toilets and say something like, what was? Today was about advent of code, performance optimization, I guess. Let's see how it looks. Perf optimizations. Let's use the font SM Mono 12. And it doesn't look that bad. It's, yeah, I mean, sure. I think that could be the Although if it's not SN mono, if we pass -t to use all the terminal, yeah, look at that. It's very chunky. Okay, I think that will be the thumbnail for this video. It's getting a bit darker, so I think that's it for today. Maybe this won't be the thumbnail, but anyway, I want to finish the video now. If you haven't, thanks for watching and see you later. Bye bye. Well, actually, no, I just realized something silly. How could I have a thumbnail look so pale and boring like this if I could, you know, pass it through lolcats and add some color to this? So let's do that. And yeah, I think that looks much nicer. Yeah, I think that the colors change a little bit between, yeah, they change a little bit between calls. So yeah, this looks quite all right. Of course, performance optimizations have to look nicer as a rainbow, I guess. Kind of like my prompt that is very colorful. But anyway, yeah, now it is the end of the video. If you have been, thanks for watching and see you later. Bye bye.